Yeah.
All right, if you guys can turn to page 11, we're going to do some review from Algebra 2, dealing with complex numbers, because we're going to need it for the next section. So, complex numbers, dealing with i's. We're going to just do a little bit of practice with it, make sure we still remember some of those properties. And then you're going to see that as we move into complex numbers, we're going to kind of circle around the same ideas with Pythagorean theorem, with distance formula. We're going to see some midpoint as well. So a lot of this you've seen before, and we're just kind of making sure that we're reviewing those topics as we build into kind of topics that are a little bit more that we need. Yeah, so basically we need this to help us with some of the feature sections. So imaginary number I is defined as I squared is -1. So if you guys can just jot down a couple of these properties here. We know that the definition for I is the square root of -1. So we know that we can't take the square root of -1 for under the real number system, but if we create something called imaginary number system, we can basically solve for values that otherwise would be more difficult to solve. So we say that I is equal to square root of -1. I squared will be square root of -1 times square root of -1, which equals to -1. So this allows us to square and still get a negative in return. I cubed would be I squared times I. If you think of I squared as -1, -1 times I would just be -I. And then I to the fourth would be I squared times I squared. And I squared is -1, I squared is -1. -1 times -1 is +1. So those are the only options as we continue to increase exponents. So what I mean by that is I to the 5th power would go back to square root of -1. I to the 6th power would go back to -1. I to the 7th would be I to the 8th is 1. So basically, if you understand that this kind of cycles through every 4 exponents, we can get to any value just by counting from 1. But that's kind of a hassle if we're having to deal with larger and larger values, right? Just the hassle to have to go through and count every one until you get to the one you're looking for. So another way that we can go about finding which, if it's I to the 11th, rather than listing everything out, which we can do, it's not too bad. Another way to find which one of the I to the 11th it matches with the original 4, then we can look for the remainder. So we can either do it by hand or by calculator. So let me show you. 11, we know 11 is going to look like one of these 4 options. So we do 11 divided by 4. Okay, 4 goes into 11 how many times? Twice, with the remainder of 3. Okay, so here's the rule. The rule is when you have remainder 3 tells you that it's going to match up with I cubed. So I cubed is -I, and if we listed it out, we can also see that's what's going to happen, right? If we cycle through every 4, I to 11th is -I. Another way to do this is plug into the calculator and look to see what decimal you get. Depending on which decimal you get, that's going to line up with which remainder it is. So for instance, if I did 11 divided by 4, I get 2.75. That 0.75 indicates that it matches with the remainder 3 and this I cubed, which is negative I. Okay, so I'll go through both ways. 18 divided by 4 is 4 with the remainder of 2. Remainder of 2 is going to match up with I squared. I squared is negative 1. Or if you did just 18 divided by 4, you get 0.5, and 0.5 is going to match with the remainder 2, which is I squared. Okay, 4 goes into 67. Remainder of 3. Remainder of 3 is I cubed. I cubed is negative I. You can also do 67 divided by 4. Remainder is 0.75, or the decimal is 0.75. 0.75 is I cubed. Okay, finally, 724. So 4 goes into 74 perfectly, 181 times with no remainder. If there's no remainder, then it's going to match up with I to the 4th, which is 1. Likewise, if you do 724 divided by 4, goes in perfectly. There's no remainder. There's no decimal. So there's no decimal. There's no remainder. I to the 4th is 1. Okay, so you guys have seen that before from previous years. Just wanted to kind of give a quick refresher. Any questions there? Okay. Okay, a complex number has 2 parts. It has the real part and it has the imaginary portion. So standard form for complex number is in the form of A plus BI. Okay, so even though I represents the imaginary unit, a lot of times we treat I like a variable in the sense that it behaves a lot like a variable when we are adding, subtracting, and multiplying. Okay, so we're just going to go through the odds here because this is just review. We're not going to. We also need to be able to see if we can cover a little bit of the next section. It says perform the given operation. So here, write your answer in standard form of a complex number. So I'm just going to treat I like a variable in the sense that I'm just going to combine like terms. So let's try number 11 here. 7 minus 12i. I can drop the parentheses because there's no negative or there's no coefficient influencing 7 and negative 12. But here, I do need to distribute the negative through. Okay, I'm going to combine like terms. The 7 and the 4 goes together. The negative 12 and the negative 9 goes together. What do we get? Mm-hmm. 3 minus 21i, right? Okay, number 13. We can multiply. So we can basically FOIL. We have 2 sets of parentheses here. So I'm going to distribute the 3 through, and then I'll distribute the 4i through, and then we'll combine the like terms when we get to it. But, you know, at the outset, we are going to kind of treat that I as a variable. It's going to behave like a variable initially. So 3 times negative 8. Okay, we do see a couple of like terms here. The 6i and the negative 32i can go together. But there's something we can do with that 8i squared. What can we do with that I squared to make it a little bit cleaner.
Make it a -1.
Good. We know I squared is -1. I can make this 8 times -1, which is really a -8. So now I can merge that -24 and the -8 together, and then the i's will stay as i's there. So -32. (6i minus 32i) gives us -26i. Okay, try 15. Okay, so this is what we call conjugate pairs, because you see how these are virtually the same binomial. It's just that I'm changing the sign. One is positive, the other is negative. When that happens, that allows things to clean up very nicely. The middle term should drop out, and we're just be left with the 2 outer terms. So here I just want to prove to you that the middle terms, they do drop out, right? They're matching values with opposite signs. So the positive and negative will drop out. What can we do with this -25i squared? Yep, so this becomes what?
25.
Positive 25. Okay, so this gives us 9 minus 25 times -1, which is 9 plus 25, which is 34. So this is going to be a future, I mean, you've seen it already, but this is a way to get rid of that imaginary unit, especially if we're trying to rationalize the denominator. We can multiply by the conjugate, and that's going to allow for this nice cleanup process for the i's to disappear, at least for that portion of the expression. Okay, so 2 factors that are exactly the same multiplied together. So that's what number 14 is. Well, yes, number 14 we didn't do, but if I have the binomial that are exactly the same, the imaginary unit will not cancel out. It's going to get doubled. But 2 factors that only have signs in the middle change, these are conjugates. So just draw an arrow to that. So which product is an entirely real value having no imaginary part? We see that here, the imaginary unit is not going to go away, but here, when you're multiplied by the conjugate, you are going to get the imaginary portion to completely disappear, as you can see here. Okay, this is generalize it as a formula by simplifying a plus bi times a minus bi. So here, this is going to formalize to just be a squared plus b squared. And you can see that here, right? 3 minus 5i times 3 plus 5i, which is really just going to end up being 3 squared plus 5 squared. Right? 9 plus 25 is 34. So when I have this, it just ends up kind of looking like a Pythagorean theorem relationship there. Right, we can show that proof there. If I were to distribute everything through, I can prove that that is the case. Middle term goes away. I squared becomes -1. 2 negatives cancels out. I'm left with that a squared plus b squared. Okay, back page, page 12. Give you guys a moment to copy that down if you're still working on that. Okay, so page 12 here. Everybody good? Okay, so state the conjugates of the given complex number. So conjugate just means you're copying down the exact same binomial, you're just changing that middle sign. Okay, so we're not going to multiply it out just yet. We're just going to name the conjugate pair. And again, you're just changing the middle sign. Don't change anything else about the second pair. Okay, so number 19, use the conjugate of the denominator to rationalize the denominator for the following fractions. So here, I'm going to identify the conjugate for 5 minus 2i, because the conjugate for 5 minus 2i will allow the I to kind of get moved to the numerator portion. Okay, so okay, what's the conjugate pair for 5 minus 2i? 5 plus 2i. So we're going to multiply the numerator and denominator by the conjugate. Make sure you're not doing a 1 minus I here, okay? Once you have to identify that conjugate, you're going to copy it down exactly in the numerator and denominator, and we're just going to FOIL out both the numerator and the denominator. Okay, so FOIL this out. And again, if you can FOIL everything out, but once you get to conjugate pairs, that little bit of a shortcut is that you just know it's going to be the first term squared and the second term squared with a plus in between. Because we know that the 2i times 2i will give us 4i squared. The I squared will push this to become a positive. So it's just going to feel a little bit like this Pythagorean theorem, a squared plus b squared, 5 squared plus 2 squared. Okay, the numerator we can clean up a little bit. The two middle terms can cancel out, or it can combine. 5 plus 7i plus 2 times negative 1. So combine some of my terms here. 5 minus 2 is 3. 3 plus 7i. So we have 3 plus 7i all over 29. Okay, and if we want to separate them into a plus bi, we can write it this way as well. They're the same thing, it's just want to show that we can represent it as separated between the a and the bi. Okay, number 20 is the same idea. See if you can go through those steps. Oh, I'm sorry. Sorry. I should have multiplied by the conjugate of the denominator, not the numerator. My bad. Should be -3 minus 7i. Okay, we're multiplying by the conjugate of the denominator, not the numerator. -15 minus 42 is -57, and -35 plus 18 is -17i. Okay, we can break this into separate fractions. Okay, graphing a number on the complex plane. It's going to look a little strange, but really you're just going to treat the first number, the real portion of your expression, as the x value, and then treat the imaginary portion, with the I attached, that as your y value. So think of the the real portion is the x value, and then the imaginary is the y value. So if I want to graph 4 minus 3i on this complex plane, you're really just going to, essentially, you're just plotting 4, -3. It's just that we have a different orientation and different name for this coordinate plane, but it's really a complex plane. Okay, so that means I'm just going to go 4 units over, 3 units down, and that's going to be my 4 minus 3i. And if I want to find the absolute value of 4 minus 3i, think of it as Pythagorean theorem. You're really just finding the hypotenuse for that triangle. So it's just basically Pythagorean theorem, right? A squared plus b squared equals c squared. Basically, your absolute value is just the distance. So imagine you're just plotting the order pair and then using Pythagorean theorem to find the hypotenuse. It really is as simple as that. And I'm just always just going to leave the negative out of it, because I know that once I square each of these terms, they're always positive. So there's no need to enter negatives in the calculator. However, if you do want to enter into your calculator as negative, make sure you put it in a set of parentheses. Okay, otherwise the calculator won't get you what you want. If you really prefer to put negatives inside, then you have to make sure they don't just say -5 squared. You have to put -5 in its own set of parentheses. Otherwise, the calculator will only square the 5, and it's not going to realize that you want the -5 to be squared. It's going to square the 5 and still keep the negative. So what I do is I know it's becoming positive, so I'm just ignoring the negative each time I'm doing that. Okay, see if you can finish off 23 and 24. Yeah, okay. Okay, page 13. All right, so reviewing some of the things that we've learned these past few sections. Where have we been this year? We've learned right triangle trigonometry. Right, if I want to find x and y, I can use cosine and sine to help us isolate that x and y. Use SOHCAHTOA. Cosine of my angle is equal to adjacent over hypotenuse. If I want to solve for x, x is equal to 9 cosine 55, right? I can just cross multiply and think of this as cosine over 1. And the rest is just calculator. So we'll skip that part. You want to just, make sure we still remember this there. So if I want to figure out y, I can use sine, right? Okay, vectors. We also see a similar relationship with Pythagorean theorem and circling around the same idea. For a bird flying 20 meters west and 35 meters north, find the resulting magnitude and direction. So magnitude is Pythagorean theorem, direction is inverse tangent, right? So bird flying 20 meters west, that's left 20 and up 35. Magnitude would just be finding the hypotenuse, right? A squared plus B squared equals C squared. Direction, inverse tangent. Okay, we'll be in degree mode. What adjustment do we have to make once we find theta? Yeah, 180, right? We have to make sure we are landing in the correct quadrant here. Sorry. Okay, as a review, polar coordinates, converting polar coordinates from order pair into polar form, we also use the same idea here, right? Pythagorean theorem will get us to that radius. Okay, so we're cycling through the same nodes, similar nodes that we just did on the previous page. Rectangular form. Okay, complex number in rectangular form or standard form is a plus bi. If I want to graph something in complex number form, just know that your first number, your real number component, is going to go on it's going to be your x value, and then your imaginary component is going to be your y value. Absolute value is also known as the modulus. That's just Pythagorean theorem, how we've been working through that. So if I have absolute value of a plus bi, that's really just finding the hypotenuse. Square root of a squared plus b squared. Okay, so graph each number in complex plane and find its modulus. In other words, find the distance. In other words, use Pythagorean theorem. Okay, 8 minus I, so that's 8 units over, 1 unit down. Find the modulus, so absolute value of 8 minus I. Pythagorean theorem. Okay, try number 2.
Yeah, can you just go back up to number 3 right quick?
Mm-hmm.
Thank you.
Mm-hmm.
Attention students, when the bell rings, please proceed to your 7th period. When the bell rings, please proceed to your 7th period.
Okay, tomorrow we'll do distance and midpoint, and then we'll cover the rest that we need to cover. We're going to have a short check-in quiz on Wednesday, but it's just 4 problems. We'll go over those 4 problems exactly on Wednesday, and then we'll take the quiz. So you guys don't worry about it. You'll do fine. Just go through the notes. Okay. And a lot of this is circling around ideas that you already know. Okay, we'll pick up tomorrow.